Eighth lecture on AC alternating current. Today we shall consider a circuit consisting of L, C, and R, which is not very frequently found in textbooks. We consider a circuit like this. This is called an inductor of inductance L, a capacitance of capacitance C, and a resistor of resistance R are connected in parallel, and the combination is fed by an AC signal. This is our problem. Now, since the circuit elements are connected in parallel, the same voltage is applied on the across the ends of all the circuit elements. So we should talk about the reference voltage V. If I be the current phasor at a particular instant, then current is divided into three parts: IC phasor, IL phasor, and IR phasor. These are the current phasors. So the Kirchhoff's voltage law in the phasor form is IL plus IC plus IR is equal to the total current phasor I. So this current is divided into three components. If we use the current equation is first we shall add up differential solution of differential equation, solution of dE. Then we write IL plus IC plus IR is equal to I is equal to I0 e to the power j omega t. Now for IL we know that VL is equal to L DIL dt, which leads you to IL is equal to 1 upon L VL dt. So this is 1 by L V dt, same V because the combinations are connected in parallel. So same V is IC is equal to, we know that VC is equal to QC by C, which leads to IC is equal to C times dVC dt, and similarly we write C dV dt, and for R this is V by R is equal to I0 e to the power j omega t. On differentiating this expression with respect to time, we get a second order differential equation whose first term we write this one first, d2v dt2, then this term plus 1 by r dv dt plus 1 by L v is equal to j omega I0 e to the power j omega t, whose CF is complementary function is C v double dot plus 1 by R v dot plus 1 by L v is equal to 0. We rewrite it as v double dot plus twice b v dot plus omega 0 square v is equal to 0, where twice b is equal to 1 upon RC, and omega 0 square is same as for series circuit. The Pi is V as a function of t is equal to e to the power minus bt a e to the power plus b square minus omega 0 square t plus b e to the power minus b square minus omega 0 square t. Whatever the relative magnitude of b and omega 0, dies of exponentially, decays exponentially because of the predominant factor thus. So in the long run, the CF contributes nothing. Either it dies down exponentially when b square is greater than omega 0 square, or it dies off exponentially as sinusoidally, dumped sinusoidal in a dumped sinusoidal nature when b square is less than omega 0 square, and dies critically when b square is equal to omega 0. However, the case in all the three situations, voltage decays exponentially with time. So we come to the PI. PI, ultimately the voltage starts oscillating with the frequency of the external source, so omega. So we write V as a function, instantaneous value is V0 e to the power j omega t, and use this in this equation. So we get minus omega square c plus from this j omega r plus 1 by L V0 is equal to j omega I0. We have neglected the e to the power j omega t term as usual. So we get V0 is equal to j omega I0. This part j omega r plus 1 by L plus minus omega square c. If we divide both numerator and denominator by j omega, this expression becomes I0 1 plus r, plus this term is plus omega c by j. Or we can write it as I0 1 by r plus 1 upon j omega L plus j omega c. We call V0 or we call V0 is equal to I0 by Y, where Y is the admittance, is defined as where Y, keeping some space, Y is equal to 1 by R plus this is XC minus XL. We call it as you see, in the case of series circuit, the phase angle for series circuit, let me first write it like 1 upon XC minus 1 upon XL by 1 upon R. For series circuit, we have, remember that tan phi is equal to XL minus XC by R. So we see that when all the circuit elements are connected in parallel, the role of L and C gets interchanged, and instead of opposition, inverse of opposition comes, and we finally get the value of V. So we write it as I0 mod Y e to the power minus I theta. So instantaneous value of voltage is I0 by mod Y e to the power j omega t minus theta. Now let me come to the discussion of theta first. When omega tends to 0, this numerator tends to minus pi, minus infinity, and so the for tan theta is equal to omega c by 1 upon omega L by 1 by R. As omega tends to 0, theta tends to minus pi by 2. As omega tends to infinity, theta tends to plus pi by 2. At omega is equal to omega c is equal to 1 upon root of LC, theta is equal to 0. So the variation of theta is something like similar to that of in the case of parallel circuits or phase. In the case of series circuit, we denote the phase by pi, and for parallel circuit by theta. This is a variation of phase. Now we see that below the resonance frequency, the theta is negative, and if we come to the V expression, V at t, this V at t is equal to I0 mod Y e to the power minus j omega t minus theta. So we can write for omega less than omega 0, theta is less than 0, and V is equal to I0 mod Y e to the power j omega t plus mod theta. At omega is equal to omega 0, theta is equal to 0, V is equal to I0 mod Y e to the power j omega t. And for omega greater than omega 0, theta is greater than 0, and V is equal to I0. I am always using this expression mod Y e to the power minus j omega t minus theta. So we conclude that here V leads. V and I are in phase, and V lags behind I. And you see another thing, that at omega is equal to omega 0, this part is the denominator is 0. The denominator is 0, so y has a maximum. So at omega is equal to omega 0, y has a maximum. As y has a maximum, I passes through a minimum. So if we see the variation of y with frequency or mod y with frequency, the unit of mod y is mho, and this is at omega is equal to omega 0, this part is 0, so this value is 1 upon r simply. Sorry, the curve will have a just opposite trend. The curve will have just an opposite trend, and this is 1 by r. Sorry. Now we can come to the same conclusion from the Phasor diagram method, which I am going to demonstrate now. Now we know that these circuit elements are connected in parallel. So we must think how the current to the circuit element behaves or responds to a reference voltage. And we we know if this is be the current phasor at a particular instant, this will if this is be the voltage phasor at the particular instant, since the circuit elements are connected in parallel, same voltage is applied, so we take the property of the circuit elements with reference to a standard voltage. So this is IR. This is IC. IC is V phasor by JXC, and this is IL phasor is equal to V phasor here will be a minus sign. So if we write this explicitly, this part becomes Now we come to the first case for omega less than omega 0. For omega less than omega 0, at omega is equal to omega 0, IC and IL have the equal magnitude. At frequencies less than resonance frequency, this part dominates over the IC. So we have this is applied voltage phasor, this is the IR phasor, this is IC phasor, which is smaller in magnitude, and this is IL phasor, which is higher in magnitude. So the circuit effectively becomes, this is IR and this is the resultant of IL and IC. So if we add, this is the resultant current I, and this is also the phase angle of V. So this angle is theta, so V is ahead over I by an angle theta. And you also see that here the circuit is inductive. Note that for frequencies less than resonance frequency, a series circuit was capacitive. Here it is inductive. We have already mentioned that the role of L and C are interchanged. IL and IC phases have the same magnitude, the circuit. This is the direction of V or phasor V, and also this is the direction of IR. So V and I are in phase. Thirdly, the circuit diagram, the phasor diagram is this. Here IC will have a larger magnitude. So the circuit effectively becomes IR and also the direction of V, and this is the vector sum of IC and IL. Since IC is bigger, it is in the direction of IC, and this is I. So we see that V lags behind I. And we can define current gains and other things. So by this we end our 8th lecture on AC, and the last one, in the next lecture we shall study what is known as the rejector circuit. Now the rejector circuit is commonly known as the parallel resonance circuit.